good afternoon and warm welcome to everyone joining the class series on emerging technologies, with the theme for today being New Space, Cube Satellites and Earth Observations. Organized under the aegis of India-Israel Forum, it is jointly convened by the Ananta Aspen Center, Confederation of Indian Industry CII, and the Tel Aviv University. This series is an initiative to promote academic linkages between India and Israel by enhancing technical knowledge and awareness about emerging technologies among college students in India. These masterclasses are possible thanks to the generous support of Triveni Turbine Limited. This is the inaugural class of the third edition of the series. 3 more masterclasses are planned in this academic year, and we do look forward to your participation in these classes as well. We are delighted to have Professor Colin Price, Head of the Environmental Studies Department, the Porter School of the Environment and Earth Sciences at the Tel Aviv University. Professor Price holds the Jose Goldenberg Chair in the Planetary Physics. He is a well-known atmospheric physicist specializing in the Earth's weather and climate, with a focus on thunderstorms, climate change, and natural hazards. A very warm welcome to you, Professor. We are so happy and glad to have you with us today and do this masterclass. We will begin with a 45-minute presentation by Professor Price and then open up to the question and answer round. I would request all of you to please keep sending in your questions throughout the session and not to wait until the end. We will be taking up your questions during the second half of the session. If you're watching this session on Zoom, please use the Q&A portal at the bottom of your screen. And if you're on Facebook, please write your questions in the comment section. It is my pleasure to now invite Professor to please start his presentation. Over to you, sir.
Thank you very much for that nice welcome. Can you see my screen?
Yes, yes.
And hear me? Great. So I'm very happy to be here today, and I'm going to be speaking about new space, Cubesats, and Earth observations. Maybe let's start with the new space, and I'd like to tell you that we're undergoing a revolution today in the space industry, especially the civilian space industry. If we look at the old space relative to the new space, when we talk about old space, we're talking about the space industry where there were a few big national players like NASA, the European Space Agency, the Indian Space Agency, Japanese, maybe some big companies like Boeing, but these were very huge entities which could eventually build satellites which may be the size of a car or of a bus. You can see here the Hubble telescope and the size of a school bus at the bottom. So some of these big satellites are very large and take huge amounts of money, more than hundreds of millions of dollars to build. You need a dedicated rocket to launch them. Most of these designs are one of a kind. They get designed completely from scratch each time we launch one of these big satellites. It may take more than 10 years to build them, and you need hundreds of engineers. But in the last 10 years, we've seen a revolution into the new space arena, where anyone can build these, not just the big players, but even high school students and university students can be part of this industry of the civilian space. Startup companies. The size of these satellites are tiny, the size of a shoebox. You can see this person holding one of these Cubesats. You can see another one up here. So these, you can see the size, it's kind of the size of a shoebox or a milk carton. The cost, including the launch, is less than, say, $1 million. So it's still a lot of money, but a lot less than the old space. To get to space, we don't need a dedicated rocket. We use kind of a hitchhiking or going up to space on a target of opportunity with another rocket, which is taking other supplies or satellites to space. So it's a lot cheaper. A lot of the hardware is modular, off the shelf, and so we can actually buy things even online. You can get parts in it. There's a lot of heritage. Other people have used the parts, and so it's quick. You can build them fairly quickly. Less than 2 years from your idea to have a satellite to the launch, and you can have less than 10 students working on a satellite, unlike the hundreds of engineers in the old space. And this is what we call disruptive innovation, because we see that it's, in some ways, it's putting out the big old space guys out of business. The same as telephones, smartphones today have put out the landline phones and the cameras, for example. On our smartphones, we have cameras, and nobody's really developing film anymore. And Kodak went out of business fairly quickly when smartphones came around with good quality cameras. And so we're seeing a similar thing in the space industry, that disruptive innovation, because of this standardization of the size and the hardware of the satellites, of these Cubesats, these small, and we call them Cubesats because they're made out of these 10 by 10 by 10 centimeter cubes. So you have these cubes which you can have a 1 unit, 2, 3, 6, 12, as many as you want by putting them together. Inside you have your computer cards, you have your batteries, maybe your sensors. On the outside, we normally put the solar panels to generate energy and to charge the batteries, but everything is standard. So the actual size and the mechanical aspects are standard. They weigh very little, 1.33 kilograms each one of these cubes, and the electronics is standard based on the PC 104 format. The computer brains and the batteries and the attitude control, all of these are modular now, and we can buy these from companies which specialize, and we don't have to redesign everything when we want to send up a new satellite. And as I mentioned, the school kids and high school students can build these. You can see the size of, this is a 1 cube, this is a 3 cube satellite, sorry, a 3 units satellites with antennas which will fold out in space. You can put your sensors on the side. And so this is really causing a revolution in how we use space and how we also look at the Earth from space, and the business opportunities of using space when we can do this from a startup company, a small company. We don't need to have huge budgets and huge amount of manpower to go to space and to study what's happening on the Earth. The launch I mentioned, this is kind of a piggyback launch, hitchhikers. You can see these huge rockets which go up to space, but if you look in these little blue boxes on the sides, there are a bunch of these smaller satellites which are on the sides. Also up here, this is the SpaceX launch this year in January, where 143 satellites were launched by one rocket. This is for the future internet from space. So some of the ideas, Elon Musk, for example, SpaceX, but OneWeb as well, they want to put these small satellites up in space, many of them, to give us internet coverage from space in any location on the planet. So that if you're in the middle of the Sahara Desert or middle of the ocean, you'll still be able to get your internet connection from space. And so this is becoming, there's a lot of competition here to get to space and to provide services to the public around the world. Besides the launch on the rockets, which then they get kind of released in space, another way to get launched is to send your satellites up to the International Space Station. And we send them up in these kind of boxes, these unit boxes. And again, this is all modular, so you have to design your satellite to fit into 1, 2, 3, 4 of these slots. And this goes to the International Space Station, and then the astronauts will release this, and you can see 2 satellites being released here from this pod in the International Space Station. Tel Aviv University launched our first Cubesat in January of this year, and this is how it was launched. It was taken up with a supply module to the ISS, and a week or 2 later it was released into space by the astronauts. So this is a new space revolution, and the nanosatellites, cube satellites, is really becoming a revolution. And we can see this taking off just in the last decade. Here we can see the number of launches of these satellites. It's increasing exponentially here. And not only for looking at the environment and the climate and the surface and Earth object observations, which interests me as a university professor, but there are also business opportunities. So here you can see some things we can do if we have data from space on a business-wise. So for example, monitoring port activity. So here's an image, for example, from Rotterdam in Holland. And we can use satellites to survey the container traffic, the storing or the stacking of raw materials like iron ore in this image, or the number of vessels at the port, how many ships are coming in, how many are leaving. And then your analysts can actually estimate the port revenue growth. How are things changing over time? Can develop macroeconomic indicators of the health of, say, the European Union here, based on the ports, say, in Europe, but this can be done anywhere in the world. And as you can see, we can see the commodities, whether it's coal or iron ore here sitting, the piles of it on the ground. And this can be observed on a daily basis from space. Another application is in the oil industry. Here we can see the satellite imagery of an oil refinery in North Carolina in the US. And the analysis of the refinery can measure the throughput of oil and gas, how much is being stored, how much is being sold. And what's interesting here is the satellites can, first of all, measure the number of tanks, of oil tanks, which you can see here, the construction of new tanks, but also how full are the tanks. It turns out that when you have gas or oil in these tankers, you actually have an adjustable roof because you don't want gas to collect under the roof when you're taking out the liquid. So the roof actually goes down and sinks on top of the liquid inside. And if you look at the different images here from September 2003 compared with March 2004, the shadow, if you look at the shadow in these tanks, this tells you the height of the lid of the channel. And so you can actually convert this to something about how much oil or natural gas or other products are actually being used and are going through this refinery. So if you want to look at your competitors, you can use satellite images to monitor what's happening in oil refineries around the world. And another application is if you want to look at your competitor, here's an image of a shopping mall, the Walmart shopping and parking lot in the United States. And you can simply count the cars parking outside. And this will give you some information about how many people are coming to shop on different days of the week. And again, you can monitor the visitors and on average, the buying amount at your store. And you can use this also for developing various economic models for yourself or understand how your competitors are doing. So this new space is becoming a huge business. There are many opportunities here. 476 companies have received investment just in the last year. As you can see how this has increased dramatically since 2010, 2011. There are many companies which are focusing on just the satellites, through more than 300 companies on the launching of these satellites. Companies which are talking about media and education, looking for interplanetary research, studying the biosphere using these satellites, information and research, logistics. It's a huge business which is expanding dramatically and will continue to expand in the future. Investment in this space is more than $22 billion in the civilian space in the last few years. So this is really something which has just started recently and it's going to be with us for a while. And this is some developing technologies which are really changing the way we work in space, both business-wise and academically on the scientific side. So now I want to talk more on the scientific side of Earth observations, because this is the field of my research. And now with all of the discussion about climate change and environmental sustainability, space can also be used to monitor the Earth and to give us data about what's happening on the Earth. We can also look at the atmosphere. We can study greenhouse gases in the atmosphere, particles, air pollution, but also we can look at clouds, which have an important role in the energy balance of the system, also for rainfall. We can monitor the oceans and ice in the ocean, sea ice, the vegetation, deforestation, agriculture, many different facets here that can be monitored using satellites in space. So I want to talk a little bit about this now. And when we're talking about measurements from space, we talk about remote sensing. The meaning of remote sensing is, as it says, we're sensing the Earth from a remote distance. We're not actually touching things or close in situ inside the medium. And so from satellites, we basically are doing remote sensing. We're trying to understand the Earth by sensing from afar. And sensing from afar, we'll see how far. But once we have a satellite, we can develop two general types of sensors which are used. There are others as well, but generally in this talk, I'll talk about active sensors. And active sensors are where you actually have to transmit a signal and then receive it in return. And by the difference between what you transmit and what you get back, we can try to interpret what we're actually seeing or the changes at the surface So for example, a radar, a meteorological radar, which tells us where we have rain on the ground, we have radars on the ground, but we can also have them in space. And then we can get information about radar. We can put lasers in space and look at the scattering of particles, dust storms, air pollution. Looking at the sea level, again, we can send a beam down to the sea level and return it and say something about changes in sea level. Even the wind, we can estimate the wind speed at the surface by looking at the reflection of waves. And if it's a smooth ocean, we'll have a different reflection to a very stormy ocean. Those are the more complicated satellites. Another group of them is the passive sensors. And the passive means that we don't send a signal, we only receive information. And normally this information is reflected light from the sun. The sun can be reflected off the surface, so we see what's coming back to the satellite, or emission from the surface, whether it's from the warm surfaces or the oceans or clouds or even fires. So active sensors, we actually have to have something which is sending out a signal, which we then get back and we can interpret it. The passive sensors are only receiving information and not broadcasting anything. Now let's talk about the two main types of satellites. And there are two main orbits of satellites. The first one is what we call GEO for geostationary orbit or geosynchronous orbit. These satellites are very high up in the atmosphere, 36,000 kilometers above the Earth's surface, and normally they're above the equator. And the reason they're that high is because at that altitude, in order to balance the gravitational force on the satellite and the centrifugal force, which is pushing the satellite out, the satellite moves at about 3 kilometers per second. And this implies that the satellite will actually do one rotation every 24 hours, exactly the same rotation as the Earth. And so because of this, as you can see in the animation at the bottom right, the satellite will always remain above the same footprint on the Earth. And so although they're both moving, for us it looks like a still image, that you're looking either at, in this image, over South America constantly, but they're geostationary satellites above India, giving you an image of India all the time. And so the benefit is we have a constant view of the same footprint on the Earth. And in fact, depending on how rapidly you image the area, you can get images every minute, every 15 minutes, every hour. And then you can generate also kind of an animated GIF to get to movies of how things are changing on a fairly rapid time scale. The problem with these and everything has pros and cons. So the cons of the geostationary satellites is that they're so high up that the footprint isn't so great. We don't have very good spatial resolution. So we do have high temporal resolution. As I mentioned, we can image at even a minute resolution, but low spatial resolution of maybe a few kilometers every pixel on the ground. So we can't really monitor the streets in the city maybe, or vegetation at very high spatial resolution. But we get very good temporal resolution if we want to look at clouds developing. And so we can develop animations to look at storms and how they develop. And another problem with the geostationary is that they're all located around the equator. And so they don't have a very good view of the poles, of what's happening on the North Pole and the South Pole, especially with the melting of ice caps, for example. And so not ideal for that. Here we can see two images using the US GOES satellites, which are geostationary satellites. So the one sits over, as mentioned, somewhere here over the equator and South America. And so we get the whole hemisphere. We can see in every image, we can see the whole disk, but only this view of the two Americas constantly. We don't see Africa and India. There's another one which is more of the Pacific, which is seeing mainly the Pacific Ocean. And so these are good because they give you a very broad view of what's going on below, but you're looking at the same location all the time. The second type of satellites are what we call LEO, L-E-O, or low Earth orbits. And these can range from 400 kilometers up to about 800 kilometers above the surface. Because they're lower down and the gravity is stronger, they need to actually move faster to stay above the Earth and not to fall down and to have the centripetal force pushing them out. So they travel at 8 kilometers per second and not 3 kilometers per second. And this implies that they actually do one orbit around the planet every 90 to 100 minutes. So every hour and a half, the satellite will come back around the Earth. And so for the satellite, it may see sunrise and sunset every 90 minutes. And these LEO orbits can be put really in any inclination, so they can also go over the poles of the Earth. And so these are the satellites we use to try to look at what's happening in the polar regions. And we can get maybe an image every day. So if we're looking for melting of ice caps, that's good enough. And the problem is that they have poor temporal resolution for individual locations. So we have good spatial resolution. Because they're low down, we can see fine spatial resolution. But as you can see, the Earth is turning underneath the satellite. And so every orbit, we're seeing actually a different location. And in order to go back to the same location, it may take a week or two to get exactly the same image. So we have low temporal resolution, but high spatial resolution. So as you can see, every type of orbit actually has its pros and cons. So we have these two sets of orbits, the GEO, 36,000 kilometers, which are mainly going around the equator, and the LEO, which are normally going in the polar orbit and are of hundreds of kilometers up to about 800 kilometers. And each one, again, has its benefits and its deficits. And I'd just like to show you this animation, if it works, of what's called stuff in space, which is tracking the satellites which are in space. And you can go in and look at yourself. It's quite amazing that there are institutes which are tracking all the satellites in space. You can see this rotating now. Every point here, and I can zoom out, every point here is some body of either a satellite or an old rocket or space debris in space. You can see the ring of the geostationary, 36,000. And if we come in close, you get to the LEO satellite. And you can actually see, if we zoom in, that they're actually moving. And if I click on one of these, it'll tell me on the side that this is a piece from the Cosmos 506. There was launched in 1972. It's still in space and its orbit here is its furthest from the Earth at 1,500 kilometers, 1,300 the closest. Its altitude 1,400. Its velocity, etc. The different colors are the satellites which are active or not active anymore, and some are debris. So it's actually very interesting here. If we go and see, for example, over India now, what's happening today. If we click on something close to Delhi here, we've got now this piece going above you, which is around about 874 kilometers, traveling at 7.4 kilometers per second. And it's something which has been up there since 1974. So this is becoming also a problem. I'm not going to talk about it today, but what to do with space debris. And we're waiting for various startup companies, and maybe some of you in the audience, to figure out how we can actually solve this problem and remove some of this space debris from space in the future. Oops. So let me go back to the slides. I'm going to stop sharing for a second. For some reason I lost that. I'm going back here. Okay. Can you see me still? My slides now?
Yes, Professor.
Okay. So I'd like to talk a little bit about types of sensors on the satellites. So first of all, we can talk about different wavelengths in the spectrum. The first one is the visible. The visible is what we see with our eyes. And so it's always nice to get pictures of things that are familiar to us. And so a lot of the sensors we use are using visible sensors, which are basically for looking at the reflection of solar radiation reflected from the surface or scattered by the Earth in the atmosphere. And we call this the albedo. The albedo is the percentage, we measure albedo in percentage, what percentage of the light coming in is reflected back to space. And this depends basically on the darkness or the brightness of the object. So for example, fresh snow will have an albedo of maybe 80 to 95% of the radiation will be reflected back to snow. But if we look at dark roads or asphalt, maybe only 5 to 10% will be reflected. The oceans are normally dark as well, but it depends on the angle of the sunlight. Forests are fairly dark, so they only reflect 10 to 20%. And so we can use this as a visible sensors to look at the Earth. And here we can see the Meteosat, the European satellite, looking in the visible in black and white. So it's a kind of an image we would see if we took a black and white image of the Earth from 36,000 kilometers. And basically what we see is we see white clouds. The brighter clouds are white. We see the lighter colors of the Sahara Desert, the darker colors of the oceans. And so this kind of, we're familiar with this, tells us something about what's happening at the moment, both on the atmosphere and the Earth. So the visible basically measures the light reflected. And so we first have to figure out what we're receiving from the sun. So most of the radiation from the sun is around about 0.5, 0.6 microns. And so we don't have to look at the whole spectrum. This image we're seeing here is looking at just one wavelength at 0.6 microns, what is reflected from the Earth back to the satellite, from clouds, from the land, from sea surfaces. The problem with the visible is that we can only see during the daytime. At nighttime, it's dark, so we don't get any information. So it's good to give us some information of something we can see and we can translate automatically. But the negative side is that we don't have any data in the nighttime. The second type of sensors are the infrared sensors. Infrared are basically measuring heat, like the heat you'll feel from a stove or from a fire. The Earth also emits heat. Any object above 0 degree Kelvin will emit heat, even ice sheets, clouds. And so using infrared sensors, we can get information about the temperature of those bodies, especially clouds and the surface. And maybe to talk a little bit about the physics behind this, black body radiation that maybe many of you have learned about in engineering or physics classes. But basically what we see here is these curves here represent the Planck function. The Planck function is the amount of energy released as a function of wavelength. And the hotter the object, the more energy is released. And you can see for different temperatures of bodies, 200 Kelvin, 300, 500, up to 6,000, we have much higher amplitudes of emission of radiation. But for this talk, what's interesting is this line which joins the maximum of these curves, which we call the Vien Displacement Law. And for those who are interested in the mathematics, we get that by taking basically the derivative of Planck function, putting it to 0, and we can get what is the temperature where we have this maximum emission. So the lambda maximum, the lambda, which is the x-axis at the maximum, depends on the temperature. And what this simple relationship shows, that the warmer the object, the hotter the object, the smaller the wavelength of the emission. So if we look at, say, the emission from the Earth, which is about 300 Kelvin, the temperature of the Earth, the main emission is around 10 microns in the infrared. But if we look at the sun, which is about 6,000 degrees, the main emission is in the visible part of the spectrum. And as I'll show in a few minutes, if we look at forest fires, the main emission is around about, the temperature is around 1,000 degrees. So it's around about 2 or 3 microns. So depending on what our target is, what we want to look at, we can design our infrared sensor to measure in different parts of the spectrum to give us information of what we're seeing. So here we can see an infrared image from the satellite, the same geostationary satellite. Now the color scale is not based on what we'd see, but the darker colors are hotter temperatures, the whiter colors are cooler temperatures. And now we can see the hot desert regions here, the black areas in the middle of the day. And we can also see the white areas, which are very cold temperatures, which represent clouds, which are very high up in the atmosphere. So infrared, we have to also design our sensors. And as I mentioned, the Earth emits around 10 microns. So the sensors looking for the Earth are normally between 10 and 12 microns, and looking what's emitted from clouds from the surface in that range. The cooler temperatures are going to be the lighter colors here, which are normally clouds. But even the oceans are going to be cooler than the land, so there'll be a grayer color. And the warmer colors, which are the hot land areas in black, are shown in the darker colors. The advantage of the infrared sensors is that here we get some signals both day and night. So even in the nighttime, we have emission of heat from the surface, from clouds, and so we can get continuous 24-hour measurements using infrared, unlike the visible. So here we can see the two images, the simultaneous measurements, the same time, the same location, visible on the left, infrared on the right. And if we combine these together, we can also learn something about the type of clouds. And I'm going to ask you a question, so get ready to answer this, and I'm going to give you a link to get into. But if we look here, you can see on the left a visible image over the United States of clouds and the surface. And on the right, we have an infrared image. And I wanted you to think of what type of clouds do you think we have in the location of the red X. And I'm going to give you a little quiz here, and let's see if it works. If you can go on your computer or your smartphone into this address on the top, polev.com/ColinPrice912, you should see this question on your screen. And so my question is, where we see the red X in this image, visible on the left, infrared on the right, how would you interpret this? Would this be a low cloud, like a small puffy cumulus cloud? Would this be high clouds, cirrus clouds? Would this be a thunderstorm cloud, deep convective? Or we can't say really, don't have enough information. So let's see if anyone can get into the website and try to answer this. And I'll wait a few seconds. If it's a problem, we'll continue. Oh, I see a first answer. So if one person got in, then others should be able to. So try to get into this, the website or this link on top, and then you can make your choice. It's anonymous, so you don't have to be worried about giving the wrong answer. A, B, C, or D. Do you think the clouds by their X, the red X on the screen, are these low clouds, high clouds, thunderstorm clouds, or we can't tell? So I'll wait a few minutes and let you put in your numbers. So far we see that this is low clouds. We have a few high clouds. 50%, 56% think it's high clouds. Deep convective clouds, we have maybe some too. I see there's a race between A and B. A is pulling ahead. Okay, so although there may still be people who haven't answered, I think because of time limitations, I'll keep on talking. You can still answer if you wish, but the correct answer is A. That these are low clouds. So how do we know these are low clouds? Because first of all, they're white, like all the other clouds. So when we look in the visible, the clouds look more or less the same. They reflect the sunlight, and it's difficult to see the difference. But when we look in the infrared, on the right-hand side, the whiter the color, the higher the cloud. And so under the red, we see it's kind of black, very similar to the background temperature of the ground, meaning that these are low clouds with temperatures very similar to the surface. Under the green X, you can see that these are much whiter, which means these are much colder. Colder means higher up in the atmosphere. And so under the X, under the green X, these are high clouds and maybe thunderstorm clouds. But under the red X, these are low clouds like fog. Maybe this is like fog close to the surface. They may be bright in the visible, but they're dark in the thermal, in the infrared. Okay, we'll continue. And that's what we can see here. If we have infrared and we have visible together, we can kind of differentiate the type of clouds. So if the clouds are very cold, but they're dark, they're not very thick in the visible, then these are thin cirrus clouds. They let the sunlight through, so we don't see much reflection, but they're very cold. If they reflect a lot and they're very cold, so they're very bright in the visible, and they're very cold, and these are deep convective thunderstorms going very high up into the atmosphere. And if we have very bright clouds, but they're warm clouds, as we saw in the infrared, then these are low clouds. And obviously, if we see dark in the visible, dark and warm in the infrared, then it's a clear area we're seeing the surface. So by combining different sensors, we can actually learn a lot. Now, how do we measure gases in the atmosphere? Well, gases we measure by looking at absorption spectrum in the atmosphere. So we need a light source here, and normally we use the sun as our source. If we look, say, at a light bulb or the sun, and we look at the spectrum, we break it up in its wavelength, we get some continuum of spectrum through the visible spectrum, for example. But solid objects have a continuous spectrum, whereas gases emit in specific wavelengths or frequencies. They have a very specific fingerprint or line spectrum. So if we're looking at a hot gas and we break this up into a spectrum, we'll have specific lines, emission lines, not a continuous spectrum like we do from solid objects or very dense objects like the sun. So now if we want to look at some cold gas, for example, carbon dioxide in the atmosphere or ozone, we can use the sun as the source and look at what gets absorbed by this gas and what's missing in the spectrum. And from that same fingerprint, we can say what that gas was. So if we look at the absorption spectrum, it'll be exactly the same as the emission spectrum for the same gas. And so if we're looking at the sun through the atmosphere, we'll get various absorption lines which tell us what we have in the atmosphere. And so here you can see the infrared absorption bands in the atmosphere. If we're looking, say, through the atmosphere, we can see that this is the transmission, 100% transmission compared with 0 transmission of sunlight through the atmosphere or any radiation with these wavelengths. And if we were looking here at this absorption band from water vapor in the atmosphere, we see there's a fairly strong water vapor band here at about 7, between 6 and 7 microns. So now if we build a sensor to look at the Earth around about 6, 7 microns, this is what we see when we look at the Earth. We see the water vapor patterns in the atmosphere. The gray areas are where we have lots of water vapor. The white areas are clouds where it's kind of saturated. And the black areas are where we have dry areas. And so we can actually see the invisible water vapor in the atmosphere by imaging the Earth in the infrared around about 6 microns. And so basically wavelength gives us information. So we can look at exactly the same images, the same location, same time, but using different wavelengths, 0.5 microns, 10 microns, 6 microns, and they give us very different information about our Earth. Here we see the visible patterns, reflection of the surface, the way we would see with our eye. Here we can get a thermal image of where it's hot, where it's cold, and here we can see where we have water vapor, even where we don't have clouds. In between the clouds, we can see the flow and the circulation patterns from the water vapor. And by putting these together with the images from geostationary, where we're always above the same location, we can develop these animations to also show the development of thunderstorms, say, over Africa, the transform of these into the Atlantic Ocean and the generation of tropical storms, cyclones, the flow patterns of the weather patterns from west to east. And this can also be used for forecasting the weather because we know the general circulation patterns. So, for example, in Europe, storms which are over Italy today will likely be in the Eastern Mediterranean near Israel in the next few days because of the westerly patterns. These thunderstorms over Africa will be moving towards the west with the trade winds, and so we can predict when they'll reach Dakar and when they'll be going into the Atlantic. So a lot of information we can get by looking at the motion of the atmosphere and how this is varying as a function of time. So let me give you some quick examples of remote sensing, both active and passive. So active remote sensing, again, we need to send out signals and get them reflected back from some object and to interpret them. So one of them is looking at sea level rise. Here, this map we can see here is actually of the average sea level relative to, say, a reference geoid between this is over a 1-year period, September 92 to September 93. The satellite will actually have to send out a radar beam which gets bounced off the ocean, and we can average this over weeks and months. And what we see is that the oceans are not flat. There's a bulge in the oceans here in the Western Pacific where the waters are the warmest. Warm waters also take up a larger volume, and so the oceans are actually about 1 meter higher in the Western Pacific compared with the Eastern Pacific. And if we plot this over time, we can actually see the increasing sea level which is occurring around the planet. The different colors are different satellites because satellites only last for maybe 5-6 years and we need to cross-calibrate them. But we can see that we see a definite increase in sea level rise. The slope seems fairly small, 3 millimeters per year, but that's 3 centimeters per decade, and you can extrapolate that out. to how sea level will change in the future, and this is likely a increase because of climate change. If we look at radar from space, we can put radars on satellites and also look at the precipitation in storms, tropical cyclones, understand how they're developing, the microphysics, rainfall, and use them also for forecasting and early warning for the public. We can put LIDARs, lasers in space, which are sending a laser beam down and reflecting or scattering of particles of smoke from fires, air pollution to know what altitude we have the pollution, and can also be used for monitoring and also warning the public about pollution events. And if we look at the passive remote sensing, looking at just what's arriving at our satellite, here again we can look at the emission of the black body temperature emissions from the surface of the oceans, and by looking, and here we can see a map of the oceans, again showing the warmest waters in the Western Pacific, but we can monitor a certain region and then look at the changes over time, showing that the oceans are also getting warmer over time, not just the air temperatures over the continents. And so satellites actually give us very good monitoring of the ocean temperatures as a function of time, especially in places where we don't have many people living. Deforestation is a big problem with climate change. And here you can see two images from satellites from 1975 to 2009. The clean areas here are areas which have been deforested and even burnt the wood here to make place for agriculture, for beef. And so this is resulting in major increase also in CO2 in the atmosphere, but having effects on biodiversity. And in next week in Glasgow, the climate summit, there's going to be a lot of discussion on how we can prevent such damage to the forest. And satellites are a key way to monitor what's going on, because not many people live in the forest. And so it's difficult to really monitor what's going on. We need satellites imaging there every day of what's happening at the surface. As I mentioned, fires. So fires, the flaming part of the fires are very hot. So we can look, say, at around about 1,000 degrees as the black body radiation from fires. And so we can develop sensors to look at fires around the planet. And we can see here, for example, the red dots we see on the map here are fires which have been detected from satellites from space. So we can see both of the smoke plumes in the visible, but with these red areas are areas where we have pixels on the satellite data which are very hot. And so we can identify them as fires. And you can see on the map at the bottom that this is a global phenomenon, the fires. Even though these are man-made fires, we can monitor them from space. And here's a little animation showing from 2001 and 2002, the changes in the fire detections over Africa. The little clock at the bottom left tells us about the months. So this is January, February. The third month will be March, April, going to December in 2002. So you can see the migration of the fires in the dry season. These are all man-made fires, or the vast majority are man-made fires, normally to clear agriculture. And in India, you know also that at the end of the agricultural season in Punjab, you have lots of air pollution because of the fires. And these fires can be monitored fairly easily with satellites from space. One of the big success stories in environmental monitoring is the ozone hole and the ozone layer. So nobody lives over Antarctica, where we know we have an ozone hole forming every year. And satellites flying over the poles and over Antarctica in the 1970s and 80s were what gave us the information that we have a problem here with the CFC gases and the destruction of the ozone layer, the ozone hole. And so because of the data from satellites, the scientists could go to the politicians and to the industry and say, we need to fix this, we need to solve this problem. And as a result, we have the banning of CFC use from the Montreal Protocol in the 1980s and 90s. And we see a dramatic decrease in CFCs in the atmosphere. And we see a recovery of the ozone hole now, which may take decades to fully recover. But satellites played a key role in detecting these problems and bringing the data and evidence to the politicians to solve this. And we hope we're doing a similar service now with satellites looking at changes in the climate, whether it's the sea ice in the Arctic or the melting of Greenland and other issues. And to end, I'd just like to point out that one of my topics of research is lightning. And so we also have satellites which are monitoring lightning from space. Here you can see this animation for a 5-year average. So the date at the top is not a specific year, but you see the migration of thunderstorms north and south of the equator with most of the lightning in the summer months. You can also see a major lightning activity in India in the summer months, and this intense band around the Himalayas with the effect of the topography. And so we can also monitor lightning from space, not just the emission from temperature, but also the optical emission from the satellites. So I'm going to end here to say that basically satellites and this new revolution we're going into with the new space, the Cubesats, we can use this at the university scale, at the high school scale, to define research missions, focus on specific topics that we want to research and analyze. We can also look at the business side and to maybe provide services, whether it's internet or monitoring of businesses or trade, also from space. And this can be done by a small group of people, a bunch of students. We don't need to have a huge amount of money, and we don't have to have the best and the most engineers in the world. And so when we're talking about Earth observations, we can use these satellites to firstly monitor the land areas like urban heat islands or major cities, the growth of cities, use it for urban planning. We can monitor changes in temperatures, the oceans, the land. We can look at the biosphere, chlorophyll in the concentrations in the ocean, in sediments, changes in the rainforests, also agriculture, the snow cover, ice cover. Besides the surface, we can also look at the atmosphere. Today we're talking about greenhouse gases, so we can monitor changes in greenhouse gases globally. As I mentioned, ozone concentrations can be monitored, cloud cover, air pollution. And I didn't mention it because of a lack of time, but we can also monitor the sun, which is the source of all the energy coming into the system. And the sun itself is a very interesting star and topic to study, both the variability of our sun, which is not constant in time. We have variations over the 11-year solar cycle, and even solar storms, which we call space weather today, which can be monitored using these satellites looking outwards instead of inwards, and monitoring changes in the solar radiation, which eventually will impact our climate. So with that, I'll end. Thank you all for listening. And as written up here, the sky is not the limit. We can go into space, and we can use these small satellites to do many interesting things, both commercially and scientifically. So thank you very much.
Thank you, Professor. That was a very interesting presentation, and I particularly enjoyed the polling session that you had. That was very interactive. Thank you for that. So we have about 10 to 15 minutes. So if you don't mind, we have a lot of questions based on your interesting presentation. So I'm just going to start with that. So the first question we have is from Mr. Varun Iyer, and he says that wouldn't the hitchhike approach alter the trajectory or path of the main rocket by affecting its weight and dimensions?
No. So these are very small. These satellites are just a few kilograms. And so the main orbit of the rocket is planned ahead of time and is based on also the thrust of the rocket. And it's taken into account, obviously. So they know the weight of the payload. There's a certain amount of satellites you can put on it. It has to be balanced as well. But this is all taken into account. But the reverse is true, that we cannot really plan the orbit, the exact orbit that we're going to get for our own small satellites, because it's a hitchhiker trip. And so we have to kind of make with whatever's available at a certain time with a certain rocket. So sometimes our satellites may go up to 400 kilometers. Maybe they'll be taken by another rocket to 600 kilometers. Maybe the orbit will go over the pole. Maybe it won't go over the pole. So we need to be somewhat flexible also. If we wanted to specifically go in a certain orbit, then it may cost us more money, or we may have to wait for a longer time until we find the appropriate rocket.
Right. I hope, Mr. Iyer, that answers your question. The next question is from Naman Ketan, who asks, what is the difference between spatial resolution and temporal resolution?
Good question. So spatial resolution is when we take a picture, what is the size of the pixel? So you can think of it on your camera when you take a picture. What is the best resolution? If you want to take a picture from space, does each pixel, is it a resolution of say 1 kilometer or 1 meter? If it's 1 meter, we can see individual roads and we can see cars parked on the streets. But if it's 1 kilometer, then we can only see maybe a neighborhood in general. We can't really see the details. So that's the spatial resolution. How many pixels do we have in our image? Do we have 1,000 by 1,000 or do we have 10,000 by 10,000? That will decide on the spatial resolution. And the temporal resolution is how often do we get the image of the same location? So if we want to study agriculture, the growth of crops, then maybe it's good enough to take an image once a day or once a week. But if we want to look at, and that's a very low temporal resolution, if you want to take an image of a thunderstorm, which develops over 1 hour, maybe we need to have an image every minute. And that's a very high temporal resolution. So the resolution is how many images we have as a function of time for the temporal, and for spatial, what's the size of every pixel.
Right, thank you. The next question is from Saurabh Kalra, who asks, how do they maintain temperature of the CubeSat?
So good question. We need thermal protection because in space, first of all, you have the satellite may be rotating, but it also goes from day to night every 90 minutes. And when it's in the sunlight, it doesn't have the atmosphere to protect it like we do. So it can go up to maybe 100 degrees C. And in the shadow of the Earth or in the dark side, it will be maybe minus 20 degrees. And so this can affect your electronics and affect how the satellite works. So this is firstly, we use some kind of insulation around the instruments which are sensitive to temperature so that there'll be less of this thermal range of hot and cold. And so this is taken into account in building the satellite. And we also test this before we launch the satellite. So we put the actual satellite, when it's ready, into a thermal chamber, a vacuum chamber, where we can also increase the temperature to maybe 100 degrees and decrease it. And then we bring it out and we see, is it still working? Because the last thing we want is to spend all this money and send our satellite to space and it doesn't work. It's dead on arrival. So we need to test it before. And by checking both the effect of pressure, it's in a vacuum basically in space, but also the hot and the cold. And then to insulate some of the key instruments with thermal sheeting so that it doesn't experience such large fluctuations in temperature.
Great. We have a few questions from an anonymous attendee. How useful are GEO satellites considering they focus only on one part of the Earth and cannot give very good imaging due to the large distance between the satellite and the Earth's surface?
Great. So, the very high satellites are mainly used for communications. So that, as you said, because they see the whole disk, we can send a message, say, from Africa to the satellite, and can come down to South America. So when we're talking about TV or telephones or communications, telephone lines, the geostationaries are used mainly for communication satellites, but also for imaging. When we're looking at the weather, we want to see the propagation of weather patterns and storms. So you're correct that spatial imaging isn't that great from geostationary. Temporal imaging is much better. So if we want to see something which is changing quickly, for example, also volcanic eruptions. So if there's a volcanic eruption, we want to see how it's developing in the next minutes, hours, that we can use for geostationary satellites. But technically, if you're talking about making money of geostationary satellites, it's mainly from communication satellites, which are transferring television channels and communication from one continent to the other.
Great. Another question from anonymous attendee is, to begin with, how does one gain knowledge about designing satellites, the technical aspects, etc.? Could you suggest some books or tell us about any workshops or organizations encouraging undergraduate students who are interested?
So we have a few summer school. We've had a summer school and some courses for kind of capacity building here in Israel. I'm sure there are plenty in India. I'm not sure about specific books because this is still such a fairly new area, but there's plenty of information, I think, on the internet. So you can go into the internet and ask for tutorials about Cubesats. There's also, I think, websites where you can buy parts of the Cubesats. So I think the internet and the web, there's a lot of it. I can look for some links to pass on to you, but I'm not sure there's a specific book at the moment. But many Universities have now various courses on this topic, and you can inquire, I think, maybe through the Indian Space Agency, where to go to learn more about this.
Gitanjali Rajulal asks, how do you understand which wavelength corresponds to which kind of information?
Good question. So this is determined often by laboratory studies on the ground. So for example, if you want to understand how to look for drought in plants or stress in vegetation, people have studied this in the laboratory by growing plants and looking at them in different wavelengths, and then trying to see where we get the best signal for if you want to look at the photosynthesis in the plant or various stress or moisture in the plant. And so a lot of research has been done in the laboratory to try to figure out what wavelength is best. And then we put this on the satellite. So we don't just kind of randomly send up sensors. And we can't look at all the wavelengths because that would be too expensive and too much data. So we really have to design this first. So we first have to do experiments in the laboratory on the ground. You could also maybe fly a drone over various agricultural fields and see with, say, hyperspectral cameras, which look at maybe hundreds of different wavelengths or colors, what the main reflectance is from various fields, whether it's corn or rice, and when they're under different types of stress. And then once you build up a model of what reflectance is, you can then translate that out to space. So there's been decades of research in these fields on the ground, and then this is translated to satellites in space.
Right, thank you. Twinkle Sharma asks, could you explain why gases show absorptions at different wavelengths?
I missed the why what absorption?
Why gases show absorptions at different wavelengths?
So gases will absorb depending on their molecular structure. And so carbon dioxide, water vapor, oxygen, nitrogen, based on the molecular structure and the chemical structure, they will react in different ways to absorption of different wavelengths. So water vapor has a specific fingerprint of what wavelengths will excite it. Oxygen or carbon dioxide, methane will be in a different part of the spectrum. So again, we have to do experiments in the laboratory to see what's that fingerprint for every gas before we design a satellite to look for those gases in the atmosphere. But again, this is based on the chemical structure of the molecules. So every molecule in the atmosphere will have a different absorption spectrum. Some of them overlap with each other, but each one has a specific fingerprint, like every human has a fingerprint. And so we can define this for every gas, and then we can build our sensor to go to space.
Great. So we just have a few more questions for you. I hope that's okay if I take another 2-3 minutes of yours. Thank you. So we have a question again on wavelengths, and it says that how can we monitor thunder from satellites by using some wavelength or using some other medium?
Thunder?
Monitor thunder using satellites, and what is the medium that is used to measure it?
So thunder we can't measure because thunder is an acoustic wave, but we can, and that won't make it out and it will decay before it gets to the satellite. But optical signal we use to monitor lightning. So what we monitor is actually the lightning flash, the optical flash, which is emitted by lightning at a special wavelength. And that wavelength will propagate out to the satellite and we can detect that. So what we do to monitor lightning or thunderstorms from space, we monitor the actual optical flash in a very narrow wavelength, around about 777 nanometers, 777.4 nanometers. And this is the emission line of oxygen. So when we have a lightning discharge, it heats up the air, which produces the thunder, but that heating of the air also causes the dissociation of all the atoms and molecules in the air in the lightning channel. And one of the key emission bands is oxygen, which gives a very bright signal around about 777 nanometers. So we build our satellite sensor in a very narrow window around 777 nanometers. And therefore, we can actually measure these flashes in the daytime and the nighttime relative to the background bright clouds.
Great. Professor, we've run out of time, and I think by the volume of questions that are continuously coming in, I think it's a testament to how wonderful and interesting your presentation was. And we are so very thankful for you to make time and join us for this masterclass. And I think I can say a big thank you from all the students who've also enjoyed your presentation a lot and have mentioned the same while writing their questions as well. So thank you very much. And thank you.
You're very welcome. And if any of the students would like to ask more questions, they can contact me offline and they can get my email either online or from you. I'd be happy to answer separately.
That would be great. Thank you so much. That's such a generous offer. And thank you so much to all our participants who logged in today. It was wonderful having you, and I hope you had a great time. Please keep watching the space for the other masterclasses, and we hope to see you again. Thank you so much, everybody.
Thank you. Have a good day. Bye-bye.